Welcome back to another HVAC Engineering-Techie training video. Today's lesson is on outside air handler control system sequences. And this includes regular ERU units and includes DOAS units, which we'll talk about in the video. Remember, this is the channel that talks all things HVAC, all the way from engineering, all the way to efficiency and performance and everything in between. I'd like to ask you a big favor to become a subscribing member if you would. If you've already done it, I appreciate it. Thank you very much. If not, just hit the subscribe button down below. Give me a thumbs up if you like the video. It's absolutely free, costs you absolutely nothing. No one will bug you. It's painless to you, but it really helps me because Google uses that data to value my videos, which keeps me on the air. So I'd really appreciate it. Thanks. So let's get started on today's lesson. All right, before we start the lesson, let's just review the videos that are available. I know you may have watched others and already know this, and we'll go through this fairly quickly. So there's C1, which is HVAC control system basics. C2, which is DDC controller network devices, the devices that actually keep us on the network. C3, DDC control architecture, talks about the different networks we use and how they're laid out. C4, DDC control components and devices. C5, DDC control installation wiring. C6, water-cooled central plant sequences. C7, hot water central plant. C8, chill water central plant. C9, constant volume air handlers. C10, VAV air handlers. C11, which is today's lesson, outside air handler unit control sequences. C12, tuning DDC control loops. C13, how to select and size control valves. C14, how to select and size control dampers. C15, HVAC pneumatic controls. Now, all of these are generic in mention. They apply to all DDC control system types. So can all be applied to every system, that no matter whose brand you're using. All right, today we're going to talk about outside air systems. Now, the main technical resource used in this presentation is ASHRAE Guideline 36-2024. It's a high-performance sequence of operations for HVAC. Also, we utilize standard industry practices. Now, we use ASHRAE mainly for the reset sequences, which has been problematic in the industry. Otherwise, they're pretty well industry standards. Normally, the design engineer describes their desired sequence of operation in standard language on the drawings or in the project specifications. However, there are problems with this that I have encountered in my career, is that new innovative design sequences never used before. So a smart young engineer will come up with a sequence that they think will really be slick and really make this system efficient and work well. But it's so complicated, or it's something no one's ever seen before, it's a problem, because without having prior experience or testing a system, it gets very difficult because the amount of testing required is extensive. I always tell a young engineer, if you're going to, I know you're smart, so if you're going to create something no one's ever seen before in the HVAC industry, then you need to put enough money in your project to be able to train everybody of what it is and how it works. And that includes the owner and his operators, it includes the programmer, the control contractor, and the programmer, it includes the commissioner, it includes the test and balance guy, it includes the contractor that's installing it. If you do not do that, it will not work. It will fail somewhere along the line because someone doesn't really understand what's going on, and they'll apply something they've done in the past from a standard system, and it won't work. And also, there's very few sequences that have never seen light of day before. I mean, we have sequences for everything, almost everything, unless you would create a new system that doesn't work like an older system, but you need to be careful because it's difficult. What happens, incorrect logic or logic components, a lot of times we don't understand, or we do, but we don't think about it, is that when we're doing sequences, there's some results, some natural feedback from the space because it's connected in series. If you're doing temperature and pressure reset together, you need to remember that they're connected in physics. And what you do with physics affects it in the opposite direction. And if you don't remember that, it'll cause you a lot of trouble. And that's why we've had so much trouble with temperature and pressure reset in the past. And Guideline 36 actually solves that, and I've tried to do that for you in these sequences. Too complex for successful implementation. I've seen some engineers create sequences that are so complicated you can't possibly figure it out. I mean, you can, but it takes forever and ever. And then in the end, because it's so complex, it's just full of errors or things that are going to mess up in the field. So we try to use a stupid principle. That's keep it simple. The more complex a sequence is, the more difficulty it's going to have remaining and providing persistence in the system. And that's the reason is because not only do we as commissioners or we as programmers have difficulty putting it in and making it work and testing it, but operators will have a terrible time trying to keep it running correctly. So simple is better. And I've always tried to convince a young engineer or any engineer, instead of creating some complex, unique sequence, why don't you see if the manufacturer already has a standard canned sequence to do what you want it to do? And the reason is because that sequence has been fully vetted and tested and works, and it'll make it much simpler for the field. Normally, control submittals are supposed to include a rewritten sequence that includes all details required to produce the desired sequence, or supply a manufacturer standard sequence that has been fully vetted for actual performance. Unfortunately, that's not the way it actually happens. That's how it's supposed to happen. Because you realize that the engineer writes a sequence in English, but programmers don't program in English. They program in the syntax of the language they're programming in, which is a lot different. So there's a lot of information that a programmer actually has to put into a program beyond that English language description of what the engineer wants it to do. There's a lot of entrance and exit points. There's timers. There's certain things that happen. There's resets. There's all kinds of things that need to go in there that I, as a commissioner, need to know to actually test it. If I don't know that, then I have to guess at what we're testing. And many times, doing that, you actually write a test that can't be successful because you didn't understand that the guy had a part in the sequence that actually affected what you're trying to test. So we need to be plain and expose what the actual sequence is going to be. But normally what happens is a control contractor actually cuts and pastes the English language sequence from the engineer's description and puts it in his submittal as a sequence he's going to do. And the reason is he's afraid he won't get approved if he doesn't do that. But it doesn't. What it means is we then have to have a separate process in commissioning that we expose everything in the commissioning sequence. So it's easier just to have the control contractor do it right up front with the engineer, the understanding that he needs to make sure that that's going to provide what he wants to do. Anyway, that's the problem we fight. We fight it all the time. Just trying to make you aware of that. All right, what sequence standards does outside air handler units need to have in them? Well, they need to have a schedule just like everything else. They need to start in time. They need to have an unoccupied schedule, what they need to do when the system's not occupied. Space environmental set points for occupied and unoccupied conditions. If the outside airflow has set points, sometimes it won't. It'll just be a single temperature, but if it has different set points, we need to know what those are. The dead band within the unit is just like any other unit. These are the standard space temperatures, which really don't apply to outside air too much, except for humidities. Standard CO2 limits, 1200 to 800 CO2 level. These are debatable, but some people want to maintain 800 CFM in the space all the time or 700 CFM in the space all the time, and that's too low. Sometimes it can just be 800 plus whatever the outside is, which is 1200. So basically 1200 is a good spot. The lower you go, the more energy you're going to use. The higher you go, the more realize that CO2 for us is a trace gas. It's not a pollutant. It's a trace gas. And it just tells us that if you have a real high level of CO2, you may have a real high level of something else. So we use CO2 to control the total outside airflow, trying to keep it free of pollutants, which CO2 is not one of them. Start-stop control, that's one thing it needs. It needs temperature control. It needs temperature reset. It needs humidity control. It may have humidity reset control, supply air pressure control, and reset for the supply air pressure. Building pressure control, return air fan sequence, relief damper control sequence if it has all those. Outside airflow control, return airflow sequence, relief damper pressure control, and reset sequence. CO2 control, outside air relief and damper control, CO2 reset control. All of those may be a component of the outside air unit, but may not be. And we'll go through this. And of course, alarms and reports and things like that. And data trends. Okay, loop tuning is really important. The things that will keep this running correctly for energy persistence, the loops need to be fully tuned. Temperature and pressure reset sequences fully commissioned and tested. Reset sequences provide energy efficiency, but without them, or if they're working incorrectly, they actually provide inefficiency, so we need to be aware of those. Space temperature and humidity set points maintained. Occupancy schedule strictly maintained. These are the things that need to happen to keep this building in its correct temperature, correct energy efficiency. And operators need to committed to maintaining these things within a facility. If these are not maintained, then the facility will not maintain its energy efficiency. The first thing we're going to look at is an energy recovery unit, an ERU. So an energy recovery unit is a unit with fans and some kind of heat exchanger device. It may be a solid, a regular aluminum heat exchanger to exchanger, or it might be it might have a paper medium in here, or it may have a heat wheel. It depends on what you're looking at. And basically what happens is we take the exhaust air streams from the buildings, we run them through a filter, and we run it through the heat exchanger to an exhaust fan that exhausts it to the outdoors. And then we have a fan in here that pulls the outside air through a filter, through the heat exchanger, and into the space for makeup air to the AC units or to a space, whatever you're doing with it. Now, these can be variable speed, but most of the time they're constant speed. Now, this heat exchanger does not allow the outside air stream to mix with the exhaust stream. So these in a heat exchanger like this, now in a heat wheel it will, and the reason is because it has bypass. The air, certain amount of air bypasses the wheel because it's only sealed with brushes. So a heat wheel cannot be used in any circumstance where the exhaust air has contaminated air in it, like from a restroom or from the soiled linen or lab or something like that. So then you would need to use an exact heat exchanger that separates the streams. Point lists for these are fairly simple. DO1 would be outside air fan, DO2 would be exhaust fan, 3 would be outside air damper, and R4 would be the exhaust damper, because we have to isolate this unit when it's not running so that outside air doesn't get into the space while it's off. And digital inputs, of course, this current status of all the fans and exhaust filter switch and an outside air filter switch. So we basically are seeing these filters, because the one problem with these, and in the past, if you've taken my other courses on air handlers, I'm not a fan of filter switches because they don't work very well. They don't really tell you what's going on. However, in an outside air unit, filter switches are important. And the reason is because it's very difficult to do an outside air unit on time changeover amount of time. It's possible, and you still need to do that. But if you live in the Southwest where I live, we have large dust storms that can impact the filters to an outside air unit very quickly. So you may have to change these filters much more often, and you may have to do it on an individual basis, not on a time basis. So that's why filter switches here can be much more important, especially the outside air one. And on the exhaust one, depends on what you have in the space. If this is a prison, boy, this can fill up really quickly. And I'm not sure I know why, but I've done several jails where the exhaust airstream is just full of cotton dust and cotton fibers, and it will just basically destroy this heat exchanger if you allow that fiber to get in the heat exchanger. So those filters also need to be changed when it's ready. And then the analog inputs is the exhaust air temperature, outside air intake temperature, and the outside air outlet temperature. Now what we're doing there is we're able to calculate the energy saved or the energy captured by that, because we know what this temperature was and we know the temperature difference here. And this temperature difference here is actually the energy that we've been able to recapture. So that's an energy recovery unit. That's what it does. So it's scheduled. The unit should be enabled or disabled based upon an occupancy schedule. During the occupied schedule, the isolation damper shall be open and closed when in the unoccupied mode. Again, we need it to be sealed when the building is not occupied. During the occupied mode, the fans will start and be off during the unoccupied mode. If after 5 minutes, either the current switch status point indicates no airflow, then stop the fan and alarm failure. So if you get a current switch failure that we're not moving air, then you know that you got a problem. Monitor the fan status continually. If the current switch indicates a failed fan for more than 5 minutes, send the level 3 trouble alarm. Monitor exhaust and outside air filter status continuously. If the filter switch indicates dirty filters conditions for more than 15 minutes, send the level 2 trouble alarm. Data trend exhaust, outside air intake, and outside air outlet temperatures continuously with an interval of 15 minutes. Now, 15 minutes is way too long to actually do diagnostics on the unit, but it's not intended for that. It's intended just to give you a look at what's going on at any point in time, so you can just see what's going on. Or if you have a problem, you can go back and look and say, well, look, this is what was happening. And that's why the 15-minute interval. Data trend exhaust, outside air intake, and outside outlet temperature continuously with an interval of 15 minutes. This is how we tell if the unit's working or not correctly. By we get this window, you can just kind of see what's going on. It's not the 15-minute interval is too long to actually do real diagnostics on the unit, but it kind of tells you what's going on. And of course, this is the energy recaptured by the unit. Now we're going to talk about dedicated outside a unit, a DOAS unit. And all that is it's a unit that provides heating and cooling, and it provides it as outside air to other units. So it may be providing units outside air to the out. It may be the DOAS may be providing outside air to air handling units, fan coil units, or it can actually be providing a large space as a single zone, whichever the engineer decides to do it. So here's a DOAS unit. So what it has is a supply fan. It has a supply fan that provides air down into the space, or if it's feeding a bunch of air handlers, it'll have some outside air dampers. Now, these may actually be VAV boxes, constant velocity VAV boxes, so they're designed to provide a certain outside air into an air handling unit that doesn't change. Or they may just be outside air dampers that are controlled by the air handling unit that has variable outside air flow requirements to it. Now, these won't be economizers, of course, because economizers will not work with a DOAS unit. I guess they would, but they kind of defeat the reason for a DOAS unit. At least I've never seen a designer do that. And what the whole purpose of the DOAS unit is to provide totally conditioned air down to these air handling units as outside air. So these units take the burden of dehumidification, take the burden of high temperature drop from outside air or high temperature increase from outside air to the air handling units, and normally we just provide 80-degree air to the air handler, which is supposed to be equivalent to return air, so that these units here never see the outside air burden. Only this unit sees it. And why that is because all these special controls and things within this unit are expensive. So if you can just provide it one time and these units don't have to do that, then your job gets less expensive. And also, this is a high maintenance issue. So you have one unit you have to spend more maintenance on than these. So that also reduces your cost because you have a single point of doing it. And that's why DOASs work and are popular. Okay, this point list. DO1 is the supply fan start-stop. DO2 is the isolation damper. It has an isolation damper over here. So it's off. It's closed when the unit's off, and it's on when it's operating. The analog outputs are cooling coil valve, hot water coil valve, preheat hot water coil valve, and fan speed. Now, it may or may not have a pre-coil depending on the environment that this DOAS is going to operate in. If it's a cold country, it'll have one probably to provide reheat. And then, of course, we have fan speed because this is a variable volume system. Digital inputs, VFD supply fan status. DI2 is a filter switch. Analog inputs, 1 is supplier temperature, 2 is supplier humidity, outside air is outside air temperature, outside humidity, 5 is room humidity, 6 is room pressure, 7 is leaving cooling coil temperature, 8 is supplier differential pressure. Now, this is the points that you actually require this unit to work. However, you may have a separate room humidity sensor that's in a common space, common return, that will provide the dehumidification control, or if every room has a humidistat in it, then you may do some high select or low select. Actually, it would always be high select, but to be able to do that, or you could use average. I'm not a fan of average because it means no one's happy, but normally you would use high select to do that. So it depends on what's the space requirement. This is an easy way to do it, to just have one thermostat, which actually provides an average. Room pressure, you need room pressure, so you need to have at least one down there to do that. And then leaving these temperatures are part of the sequence. So that's a DOAS air handling unit. Typical sequences. The DOAS air handling unit should be enabled anytime any connected air handler unit is operating. When enabled, the isolation damper shall open and the supply fan shall start. When the unit is off or unoccupied, the fan shall be off and the isolation dampers shall be closed. The supply fan shall run anytime the unit is occupied mode. If after 5 minutes the fan current switch status, or the VFD, point indicates no airflow, then stop and alarm failure. The supply fan pressure control. The supply fan should be modulated speed to maintain the supply duct pressure set point. The supply duct pressure set point should be reset by the supply air set point reset sequence. And this is a kind of a diagram that we're just saying here that the set point for the supply air is 1.5 inches. And this is the throttling range from 1.4 to 1.6. So at 1.4, the fan will be at full speed. 1.6, it'll be down to minimum speed. But normally it'll just isolate right around here. It'll operate right around here, trying to maintain set point. And remember, this set point is set during tap. Typical control sequence for cooling. During the occupied mode, the cooling coil shall modulate to maintain the occupied supply air temperature set point. So here's it. We said it's around 60. It might be lower, depending on what these units are. And its throttling range is 57 to 63. So again, valve will be closed here and fully open here, but normally it'll just isolate right around here. It'll operate right around here, trying to maintain that 60 degrees. And the heating control during the occupied mode, the water coil valve shall modulate to maintain the occupied supply temperature. Same thing with the heating side. So when it's calling for heating, the unit will be set at 80 degrees, and it might be a little higher depending how cold it is outside. So if the units, this is a DOAS unit, so it's just the outside air component. And depends on how it's designed, but you can actually use the DOAS unit to give you some boost in heating or cooling. So if it's really hot out there, and you've got a lot of capacity in DOAS, you can actually provide colder than 60 degree air, or to give it a little help. To all those units get a little help in air conditioning or in heating. If it's really cold, you can provide beyond it. You can provide 90 degrees to all the air handlers and outside air, which would help them in the heating mode. It depends. Normally we just do 80 degrees to return air, and this may not be 60 degrees. It may be a little warmer, but the reason is a lot of times we have to do dehumidification. But anyway, we'll talk about that in the dehumidification sequence. Supply air temperature should be 80 degrees and reset every 2 minutes by trim and respond control sequence to be equal to the average return air temperature of all connected air handling units. That's where we want it to actually run. If we want to boost it up and down, we can, but this is where it's intended to. And then, of course, you have a preheat coil. Our preheat coils are designed to take the outside air, which is too cold, and raise it up. And we normally raise it up to just a little bit below the cooling coil set points. So modulate the preheat water valve to maintain the preheat set point temperature of 45 degrees, measured at the leaving side of the cooling coil. If the cooling coil outlet temp drops below 38 degrees, stop all fans. Close the relief and outside air dampers and open the return air and chill water, reheat and chill water coil valves 100% and send the level 2 trouble alarm. So this coil is actually designed to take the cold outside air, which may be freezing, and raise it up. But if it doesn't do that, then we need to shut everything down because it's going to freeze these other coils. So basically we turn off the fan. When it gets to freeze protection, we turn off the fan, open these coils to make sure that we're actually using the chill water to warm it up. So here's the diagram for that. So a preheat coil is going to take very cold air and raise it to 45 degrees. And we can measure that right here because this set point is way above 45 degrees. So we can use that to control this coil as well as this coil. And then we have a heating coil here that can take that cold air at 64 and reach it up to 6 point, which we were saying is right around 66. We may get it up to 80 degrees depending on what we need to have there. But this is the throttling range of this coil. This coil has a different throttling range sitting over here. Dehumidification control. If during the occupied mode, the room humidity rises above 6% for more than 5 minutes, place the cooling coil into dehumidification mode. When the room humidity drops below 45% for more than 5 minutes, return to normal temperature control mode. In dehumidification mode, modulate the chill water valve to maintain the cooling coil leaving temperature to maintain a 50% room humidity, and modulate the hot water valve to maintain the supply air temperature set point. So this is a standard dehumidification sequence that we would do on that, which we just drop the cooling coil to wring the moisture out, and then take the heating coil to reheat the space. Now, you can always tell if an air handler can dehumidify is if the heating coil is downstream of the cooling coil. If the heating coil is only upstream, then you cannot do a reset. And normally, if you have VAV boxes down there with a heat, which this one would never have, but if you have a regular building, you can't normally use those because there's not enough heat. You need more heat. So normally, a heating coil downstream of the cooling coil there's a critical requirement to be able to do dehumidification. Freeze protection. During unit operation, if the low temperature sensor drops below 40 degrees for more than 5 minutes, send a level 3 freezing alarm. If the cooling coil leaving temperature sensor drops below 38 degrees for more than 15 minutes, then shut off the fan, close the isolation damper, open the cooling coil and preheat valve to 100%, and send a level 2 freeze alarm. The system will require an operator to verify that the freeze condition is no longer present before clearing the alarm and resetting the unit. Now, normally this would happen if the preheat coil failed, if the valve failed closed, or if the hot water is not working or the pump failed, then we would see that freezing air come into the coil. So this would normally be the condition that what happens there. Supply air pressure control. The reset sequence should be reset the supply air differential pressure using the following trim and respond logic loop from the outside air flow percentage of the connected air handler outside air dampers. The supply air pressure starts at 1-inch water gauge. So here's the reset schedule. Every 2 minutes, evaluate the system resets. If the air handler outside air damper flow is less than 90% for more than 4 minutes, then send 3 reset requests. If any outside air damper flow is less than 95% but greater than 90% for more than 2 minutes, then send 2 reset requests. If the outside air damper flow is less than 100% but greater than 95% for more than 2 minutes, then send a 1 reset request. If the outside damper flow is greater than or equal to 100% for more than 2 minutes, then send 0 requests, so don't send a request. Reset range for the supply air differential pressure shall be from 0.5 inches to 1.5 inches. See the reset parameter table for action based upon the number of resets. And this is the parameter set for that particular set. So you can see here our set point starts at 1 inch. Our minimum is a 1/2 inch now, and then our maximum is 1.5. So during balance, the tab contractor set the system up to be able to supply design air for all connected dampers, and it'd be 1.5 inch. The minimum needed to be selected by what the minimum set points of all those dampers are. And that should be this 0.5 inch. Maybe it won't be 0.5, it might be 0.75. We don't know. But that needs to be set by actual testing and not by guessing. And these are all changeable. Of course, all these numbers I provided up here are all variable. You can change them. So here's the supply maximum. Now here's the time delay. So we have a time delay when we first start in the morning of 4 minutes. And then we have a interval. Our actual time interval is 2 minutes. Because this is outside air, we want to change sooner than not longer. And then our time interval is 2 minutes. Our ignored requests are 1. And this 1 is 10%. Is 10% of your connected load, and I'm pretending that there's only 10 here because it's not an actual job. This is just a training exercise. So it's 1 because we have 10 connected units. If we had 100 connected units, this might be 10. And remember, this ignored responses are what tell us the level of energy efficiency. The higher this is, the more energy efficient we are because we're ignoring some of these requests. But the lower it is, the more responsive the system is. So we're trying to get an easy in between there somehow with the other. And they've come up with, this is the ASHRAE guideline of 10% of the connected components. Then ours are requests that we actually get. So in other words, the system actually looks at all the requests it gets. It takes that total and subtracts the ignored request, and that's the request it's going to work with within that time period. And it takes those requests and multiplies it times the set point action reset. And remember, the higher the DP, the more energy this uses. So it basically is going to say 0.5 inches. 0.05 inches is what we're going to do each time. So you take those total requests, multiply by 0.05, and then verify it doesn't exceed this limit. If it exceeds this limit of 0.15 inches, then 0.15 is the amount it will make a change during that time period. Otherwise, it'll do whatever multiplies out. You know, if you have 2, this would be 0.10, and it'll do that instead. And the set point trim is when it's got no requests, none from the system, so it down goes the other direction, and then it'll lower it by 0.15 inches. And that's quite a bit, so you realize it's 10% when it goes up and down. So the formula is if the resets are greater than the ignored request, then the formula is request minus the ignores times the reset variable, which is this one, limited to this max. That's the formula. And then if the requests are less than the ignored, which is 0, then the press trim, then you're going to trim, change the set point by this amount there. And this is a simple way that it does that. So this is basically that, you know, the reset action increases the energy utilized. And this is the general formula. Then our reset sequence looks something like this. And this is assuming that the temperature is the same, 80 degrees, where our set point doesn't change. And so that it doesn't change. This is my handy-dandy chart here. Now, this is not an actual creation, but it's designed to tell what the total time of these resets would be. Normally, this will move around very little, but I jury-rigged the resets able to give me maximum response. So it says, you know, we're going to go for the 4-minute dead time, and then we're going to start increasing. And in this case, it's going to increase from 1 to 1.15. So it's going up 1.15. And this is going up 1.15 and 1.5 until it gets to the maximum, which is our 1.5. Oops. So this goes up. This is the dead time. This 4 minutes here. And once it gets it, it starts getting its request. And I push this to get maximum request. It goes up our maximum amount, which is 0.15. And then we go over and we go 0.15 and 0.15 until we reach the maximum of 1.5 inches. And then it sits there until we get no request. We start getting 0. Then it drops this full 1.5. And it will go down, and eventually it may actually go down to the minimum 0.5 or wherever. But I'm looking at the time interval, trying to keep these timings going from top maximum down to close minimum. And I want to be able to make sure these are less than a half hour, because over a half hour is too long. Perception and the unit can start winding up, so we're going to do that. Now, that's changeable. By changing these amounts up here, you can adjust these timings by going faster. So you can go down faster, you can go up faster, depending on what you want to do. But I like this under half hour, 10 to half hour is great. Over half hour is not good. Under 10 is probably too fast. It's going to provide some hysteresis in the system. And that's just the way I look at the systems as I'm testing what I've designed it to be. So our trends and monitoring points. Data trend the supply on the outside air temperatures and supply our differential pressure continues with an interval of 15 minutes. Data trend the supply on outside air humidity and room humidity continues with an interval of 15 minutes. Data trend outside air temperature, preheat, and valve position, chill water valve position, hot water valve position, anytime the unit is running with a standard of 15 minutes. Data log runtime of the supply fan motor, reasonable for operations, for maintenance. Data log a running total of the requests generated by each zone to identify zones that are driving the reset logic. If you have one zone that's always got a problem, then you need to find out what's wrong and fix that problem. All right, so an energy recovery air handling unit is exactly like a DOAS unit, but it's designed to be able to handle a large makeup air load. So basically this could be a system that has several large air handlers, say like auditoriums or something, that have a great deal of exhaust because they have a very high outside air load, very high ventilation load. And they will use these units either as just for a single zone, very large zone, or as for a DOAS type units, other air handling units. So these might be VAV boxes, like I said before, or might just be an outside air damper on the unit that's controlled by the air handling unit it's connected to. So these do the very same thing as a DOAS unit, but they are normally a lot larger unit, and they have a total exhaust system. So here, this exhaust fan draws air out of the space through filters, and normally there's a heat wheel involved. And the heat wheel is now going to transfer, it's going to be an ERU unit, that's the ERU, Energy Recovery Unit, and exhaust that air. And then the other main fans, the supply fans, draw the air in from the outside across the filters, again across the heat wheel in the opposite direction. And they're going to get whatever energy is in the exhaust stream, they're going to try to move that over to the intake stream, and normally we're going to move about 70% or so. And then it's going to go into the cooling coil and then to a heating coil and then the supply fans out to the space or to the other units. So that's how an air handling unit works. And there may be more than one heat wheel. There may be a sensible wheel and an entropy wheel. So it depends on the different manufacturers. It has some pretty fancy operating sequences around. And that's the general operation of a ERU air handling unit. Pointless for ER units larger because it's a bigger unit. DO1 is supply fan start stop. DO2 is an exhaust fan start stop. Now these show ray fans, so there's a lot more than one fan, maybe 6, 8, 10. But normally a pointless, this will start all of them, whether they're a single VFD, all the fans are one VFD, or if every fan has a separate VFD, it's just only one set point. 3 is the outside air and exhaust isolation dampers. These isolation dampers we want off when the unit's off. We want on when it's on. And DO4 is the heat wheel bypass dampers. Now the heat wheel has a bypass damper, and the reason is when this heat wheel is not operating, there are times when we don't want the heat wheel to operate. We'll open the bypass dampers, and that's strictly there to relieve the pressure. There's no reason to have the fans push against pressure if we don't need it. So they basically open it up and allow this to be a lower pressure device. Analog outputs, cooling coil valve is 1, 2 is a hot water coil valve, 3 is a supply fan speed, 4 is the exhaust fan speed, and 5 is the heat wheel speed. So there are different conditions for heat wheels, what speed you want them in. There might be 1 speed for heating, 1 speed for cooling, and that's up to the manufacturer to determine what that is. Digital inputs, 1 is supply fan status out of the VFD, or the VFDs, whichever. DI2 is the exhaust fan status, again off the VFDs. DI3 is a differential switch for the exhaust filters. DI4 is the outside air filter switch that tell if we've got pre-filters loading up because of some kind of condition, or if we've got these loading up and they need to be changed more often than the schedule. Analog inputs is 1 is a supply air temperature, 2 is return air temperature, 3 is return air humidity, 4 is a room humidity sensor, 5 is a supply air pressure, 6 is room pressure, 7 is supply air fan status, 8 is a exhaust fan status. These can be airflow. Their status is airflow. They've got digital status, but this is the actual airflow, and these airflows are normally taken off special ring flow meters that are in the inlet of these fans. 9 is the leaving heat wheel low temperature sensor, and 10 is the leaving heat wheel humidity, which is right here, which we're going to use in the sequences. And then outside air temperature and outside humidity, which are here. These might come in from a global point, depending on what sometimes we'll put them right here to keep them right in the link for accuracy, because these do need to be calibrated often, and sometimes if they're at a weather station, that's more difficult to do. And that's the point list. Now, they can have many more points, but this is the points we actually need to operate the system. So here's the sequences. The ERU air handling unit shall be enabled anytime any connected air handling unit is operating. When enabled, the isolation damper shall open and the supply fan shall start. When the unit is off or unoccupied, the fan shall be off and the isolation damper shall be closed. The supply fan shall run any time the unit is occupied mode. If after 5 minutes the fan VFD status point indicates no airflow, then stop the fan and alarm fan failure. Supply or pressure control. The supply fan shall modulate the fan speed to maintain the supply duct pressure set point. The supply duct pressure set point should be reset by the supply air reset sequence. And this is a standard diagram saying we got 1.5 inches, which means that at 1.4 it's going to be the fans will be at speed. At 1.6 they'll be down at low speed. And of course these are depending on what the tab set or what your set point currently is. And remember, normally it'll just work right around there. Exhaust fans. The exhaust fan shall run anytime the supply fans are running. If after 5 minutes the fan VFD status point indicates no airflow, then do a trouble alarm. Exhaust fan speed control. Using the fan tracking control loop, the exhaust fan shall track the supply fan's airflow minus an amount equal to the required outside air CFM for both ventilation and building pressure control. The flow offset amount shall be reset by the room pressure sensor to maintain at least a 0.02 positive inches water gauge building pressure. Now it could be lower. It could be 0.015, which is really low, but it could be more. I wouldn't make it above 0.03. What happens if you get 0.03, 0.05, you can actually start interfering with door closers, pushing doors open, so we don't want to do that. 0.02 is a really sweet spot for that. Cooling control. During the occupied mode, the cooling coil valve shall modulate to maintain the occupied makeup air temperature set point, and normally it could be colder. For a cooling coil it might be 60 degrees. We might be trying to take some of it, but normally it would be up around 80 degrees. Heating control. During the occupied mode, the hot water coil valve should modulate to maintain the occupied makeup air temperature set point, which here we show as 80 degrees. Now remember, just like a DOAS unit, we can lower the cooling set point to give more cooling effect to all the air handlers connected, or we can raise the heating to higher than 80 degrees, and depending on what you want to do. But normally both of these would be set right around return air temperature, 78, 77 degrees, 80 degrees. Supply air temperature reset control. The supply air start temperature should be 80 degrees and reset every 2 minutes by a trim and respond control sequence to be equal to the average return air temperature of all connected air handler units. And this is one time that average actually works. You could reset. You could do a high select if you wanted to, but normally it's just reset based upon these boxes or whatever these are, these dampers position. And here's the supply air reset sequence. The reset sequence will reset the supply air differential set point using the following trim and respond logic loop from the outside. This is not temperature, this is pressure. Start that again. The supply air pressure reset control. The reset sequence shall reset the supply air differential pressure using the following trim and respond logic loop from the outside air flow percentage of the connected air handling outside air dampers. The supply air pressure starts at 1 inch water gauge, and that's just something we've selected that you may want to actually test what want that to be. Every 2 minutes, evaluate the system reset request. If the air handler outside air damper flow is greater than 90% for more than 4 minutes, then send 3 reset requests. If the outside air damper flow is less than 95% but greater than 90% for more than 2 minutes, then send 2 reset requests. If the outside air damper flow is less than 100% but greater than 95% for more than 2 minutes, then send 1 reset request. If the outside air damper flow is greater than or equal to 100% for more than 2 minutes, then send 0 reset request. Reset range for the supply air differential pressure shall be from 0.5 inches water gauge to 1.5 inches water gauge. See the reset parameter table for actions based upon number of resets. All right, so this is the actual sequence in English, and here's the reset table that will actually show you what's going on. So here's the initial set point is 1 inch, and we've just selected that. The minimum set point for the system is 0.5, and the maximum is 0.15. And this 0.15 would have been selected during test and balance to see what pressure required, that if they're all open, and they all want design flow, what pressure does that give it? But now for the minimum pressure, balance also needs to do that. We need to set the outlet dampers, the outside air dampers of all the other units, down to minimum flow. What is the minimum ventilation flow? And in this 0.5 inches needs to be a tab reading at that condition. So that's something that we don't normally do in TAB. They don't normally set that, but we will need them to on a DOAS unit or an outside air handling unit. The time delay from start is 4 minutes, just like the other one. The time interval is 2 minutes, and we're using 2 minutes here because this is an outside air system. It's constrained, so we could use longer, but this will change faster, so we want it to change quick enough to catch it. The ignored requests are 1 because we are saying here's 10% of the connected zone. We're saying we have 10 air handlers on this. So 1. And remember, the resets, we're going to receive all the resets from the system, and we're going to subtract this ignore. So the higher this is, the more energy efficient the system is, but less responsive. When this is lower, it's more responsive. R is a change request. SP rise is what we're going to do every time we want to raise the system. So what happens is we collect all the reset requests from the system, and then we subtract the ignores, and we take what's left, and we take that value, we multiply it times this value, which is CP revised. So if we have 2 of these, we come up and we have a net 2 requests, then we're going to increase the supplier differential pressure by 1/10 of an inch, 2.05s. But if we get 4 of them, we're going to have to watch it. We have a limit here, res max limit, and the limit is 0.15. So if you have more resets than 0.15, more than 3, you're going to limit you to 0.15. So it does have a limit, and by changing these numbers, you can decide how fast you want the system to go up, how fast you want to go down, how responsive you want it to be to those requests. So this is why these are all adjustable by operators or by the programmer as we go into this. So the formula, and this is the trim action, so when we get 0 requests, we go down by 0.15. So we go up and down the same if we have 3 requests. Okay, so here's the formula. If the resets are greater than the ignored request, then the formula is resets minus the ignored resets times reset V. So you just take whatever the net requests are and multiply it times this, and make sure it doesn't go over this, because this is the maximum. If R is less than ignored, which is 0, then the pressure trim equals a change set point. So it just means you don't multiply anything. It just, you get any. You get zeros, then you go down. Because what we want to do is, remember that when we reset up, we are using more energy. When we reset down, we're using less. So we want to go down fast and up slower. So this allows us to do that, because we could go down slow, we go up slow, go down really fast. So, but you can make it go down faster by making this 0.20 or something. But I've used these as an example. And here's my handy dandy chart, just like the other DOAS unit, of how I tell how long it's going to take to get from minimum to maximum. So this unit would do the 4-minute delay that's in the delay, and then it would get its request, and this time I had maximum request. It goes up maximum, 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 and then it reaches its limit, so it sits there until it gets 0 requests. When it gets 0 requests, it goes down, and then if it sits there and it gets more requests up, this only had 1 request, it had 2 requests, 2 requests, 3 requests. So you can see it can bounce around a little bit, but normally it's slow. It doesn't take a lot of change. Normally the systems don't change very fast in this regard. But what I've done is jury-rigged these resets up here to give me maximum. And of course, what I show here, that with the reset, I can get from start point to maximum 10 minutes. And it might take me 16 minutes to get in. And what I'm trying to say here is that basically I'm under a half hour. I don't want any change from minimum to maximum to take longer than a half hour. Because if I have a large outside air load change, I need to be able to capture it. And a half hour is a good rule of thumb of where to be under. What happens is over a half hour, things start, people can realize what's going on. So, because what would happen if you couldn't catch this, you wouldn't be able to change building pressure. And when the building pressure gets negative for a long period of time, people will notice, and it'll start bringing in debris. So basically, I always use a half hour for these intervals. Now remember, on this system, the temperature is actually fixed as reset by a value of all the units, so it doesn't need this request. You could put request on it, but it's a simple sequence, so I don't know why you would want to do that. Make it, remember, we're trying to use the keep it simple, stupid, right? The KISS principle. And so we want it to be as simple as possible. There's no reason to use complexity if you don't need it. So energy recovery mode. If during the operation, during summer operation, the outside air enthalpy is 4 BTU per pound greater than the return air enthalpy, then close the enthalpy wheel bypass dampers and start the wheel rotation at the summer wheel speed. If the differential enthalpy drops to 2 BTU per pound or less, stop the wheel and open the bypass dampers. If during winter operation the outside air enthalpy is 4 BTU per pound less than the return air enthalpy, then close the enthalpy wheel bypass dampers and start the wheel rotation at the winter wheel speed. If the differential enthalpy drops to 2 BTU per pound or less, stop the wheel and open the bypass damper. And that's why we needed those humidity sensors where they're at, is so we can tell what the enthalpy is going through it. We calculate enthalpy from dry bulb temperature and the humidity of the air. And those sensors are easy to use. Now, the one thing about this sequence is it is an enthalpy wheel. And to keep this operating correctly, these humidity sensors need to be calibrated often, probably every 6 months. And this thing needs to be checked every season to make sure it's operating correctly. Dehumidification control. If the unoccupied mode, the room humidity rises 60% for more than 5 minutes, place the cooling coil into the dehumidification mode. When the room humidity drops below 45% for more than 5 minutes, return to normal temperature control mode. In dehumidification mode, modulate the chill water valve to maintain the cooling coil leaving temperature to maintain 50% room humidity, and modulate the hot water valve to maintain the supply air temperature set point. Now remember, this air handler has a heating coil downstream of the cooling coil, so we can actually do dehumidification. If not, then we would be putting very cold air down to these air handling units. And during dehumidification mode, that may be okay, but it may not. So basically, you're going to reset it now. You could reset less than you normally would if you were going down into a space, but you still have to reheat, so a reheat coil is required. Now, what we normally do here, now some people have a sequence where they just want to drop the cooling coil to maximum cold, and this one will do it while the room is high, but as the room starts to drop, we want to maintain it to 50%. If you don't do this, then you will overcool the air and reheat the air, and you'll waste energy. There's no reason to do that. I mean, you might as well use the sensors you have in place to do a more logical reset that gives you some energy evaluation. Remember, dehumidification is expensive, but it's very mandatory. If you let the room humidity float up above 60%, you could be endangering people by the growth of mold if you do that. So you don't want to do that, and besides, it's uncomfortable. When humidity gets high, people get more uncomfortable, and they'll try telling you that the temperature's wrong, but it's not the temperature, it's the humidity. So you want to make sure you control high temperature conditions or high humidity conditions. Freeze protection. If the low temperature sensor drops below 40 degrees for more than 5 minutes, send a level 3 trouble alarm. If the low temperature sensor drops below 38 degrees for more than 15 minutes, shut down the supply fan, return fan, close the outside and relief dampers, open the cooling coil valve to full open, and send a level 2 trouble alarm. The system will require an operator to verify that the freeze condition is no longer present before clearing the alarm and resetting the unit operation. Monitoring points. Data trend supply air, outside air, leaving hot water, and return air temperatures continuously with an interval of 15 minutes. And these are just status points to see what's going on. Data trend the outside air, return air, leaving hot water, room humidity levels continuously with an interval of 15 minutes. And these are diagnostic in nature. Data trend the supply air fan speed, exhaust fan speed, building pressure, supply air duct pressure continuously within an interval of 15 minutes. And these are diagnostic again. Now, if one of these alarm trips and you're an operator, then you'll go check everything out. If it doesn't, you can't quite figure what's going on, then you'll need to set up another trend at maybe every 15 seconds or every 30 seconds. Say maybe every 30 seconds to do true diagnostics. It's 15 minutes is way too long to do true diagnostics, but it's there for just an operator check to see what's happening. Data log runtime of supply fan and exhaust fan motors resetable by operators for maintenance. Data log runtime of the heat wheel continuously, totaled annually. Data log a running total of all requests generated by each zone to identify zones that are driving the reset logic. So this is standard monitoring trends of all units. Now, what about CO2? What if you have demand ventilation on one of these units? Well, here's how this would happen. any room CO2 level exceeds 1,200 parts per million, then enter the CO2 control mode. When all CO2 sensors are below 900 parts per million, so exit the CO2 mode and return to standard ventilation and building pressure control mode. When in CO2 control mode, the return or exhaust fan speed or flow control should be modulated to track the supply fan speed or flow minus an amount equal to the outside airflow required to provide the required ventilation flow plus building pressurization flow as established by tab. The offset flow amount should be reset by the CO2 reset sequence. So what's basically happening, you've got an air handler that's operating, maintaining building pressure, and if a high CO2 level begins, then we want to change that amount to greater. We're not going to change building pressure, but we want more air in between it, so we're going to exhaust some air now, or maybe even relieve a little bit of air to do that. So remember that CO2 is not a pollutant. CO2 is a trace gas. It's actually a noble gas that we actually need to survive. So we use it as a trace gas because we can measure CO2 really well. We can't extract it very well, but we can measure it really, really well. So we use that to say, well, if the room has this high level of CO2, there may be other contaminants that came in with that same, whatever's causing, people mainly. We don't have enough fresh air ventilation, so there may be other things that are pollutants that we don't want in the space, so we want to keep the CO2 lower. The lower you keep the CO2, the more expensive the system is going to be. The higher the CO2, the lower it'll be. So basically trying to maintain a space at 750 or 700 parts per million is foolish. Because number one, people can't tell that level. You can't really tell the level between 400 and 1,200. You may say you can, but you really can't. I've measured it. I put CO2 loggers in space and driven clip to 3,500 parts per million. 3,500 parts per million, we start getting some feedback from the people that it's uncomfortable. But 1,200, it's not. You can't tell the difference. So basically, we're maintaining that level. That's what this sequence is doing. So the offset flow reset control, the reset sequence shall reset the return or exhaust airflow to supply fan flow offset using the following trim and respond logic loop from the room CO2 sensors. The offset flow resets starts at the flow amount required to maintain building ventilation pressurization is established by tab and is limited by an amount equal to twice that of the starting flow amount. So what this is saying is it's not going to allow CO2 to drive the CO2 past twice what the normal outside airflow would be. You're not going to drive it to clear full air handler. You can only drive it to, so we can take it, what it's trying to do is limit the time so we don't get this large inflow of temperature differential. We're going to take it over time. Every 2 minutes, evaluate the system CO2 reset request. If the room CO2 sensor is greater than 1,300 parts per million for more than 2 minutes, then send 3 reset requests. If the room CO2 sensor is less than or equal to 1,300 parts per million, but greater than 1,100 per million for more than 2 minutes, then send 2 reset requests. If the room CO2 sensor is less than or equal to 1,100 parts per million, but greater than 900 parts per million for more than 2 minutes, then send 1 reset request. If the outside air damper flow is less than or equal to 900 parts per million for more than 2 minutes, then send 0 reset request. Reset the range of the room CO2 shall be from 900 parts per million to 1,200 parts per million. Send the reset parameter table. See the reset parameter table for action based upon the number of resets. So this is a standard reset sequence like we've been saying, but it applies to the CO2 sensors. Now, one thing about CO2 sensors is they make really good sensors, they make really bad sensors. So if you don't have a really good sensor that maintains its set point over time, you're going to have to calibrate these often. Because I've seen reset sequences, I've seen CO2 sensors be off by 400 or 500 parts per million. So they will drive this reset crazy if you don't have really good sensors or if you don't keep them maintained. And here's the CO2 reset loop parameters. The set point is 900 parts per million. The minimum set point is 800 parts per million, and the maximum is 1,200 parts per million. So normally we don't want to try to maintain under this 900 parts per million, and maybe even that's too low. You might want to even set that up a little bit. The delay starts 4 minutes again. The interval is 2 minutes. The reset is 3, and we've just raised that up to get it a little bit more, or a little less responsive to the system. The minimum set point rise is 50 ppm. The reset max is 150 ppm, and trim is minus 200 ppm. So the formula again is the same. Is the resets are greater than ignores. Then the formula is R minus IR times the res times this 50. So you can see we can do, again, 3. If you have more than 3 set requests, it's going to limit it to 150 ppm. And trim is the same as if you get zeros, then you're going to go down 200 parts per million. So we're going down fast as we're going up. Standard reset sequence. And our little handy dandy table here just shows it going up. Now it can go higher, but I was just looking at the response time for this and letting know now if it had to go clear from this, I'm trying to look at the amount of flow. So this is the reset from 4,000 to 8,000. If we had to do that, it's going to take about a little bit longer than a half hour, but I'm okay with that for CO2. And so normally there won't be large changes unless you have a whole large bunch of people come into a space or take a CO2 canister and ignite it in the space, but you're not going to let that happen. So basically there are some practicalities to this, but normally we're trying to shoot for a half hour. And I was just looking, what is it going to go, if it's going to go from 800 parts per million up to 900 parts per million, it'll take care of that real easy. And that's normally kind of people type thing you will see. But it could continue to go up, and it will continue to go up at a level about like this. So it'll probably take 30, 40 minutes. It'll take a little longer, but that's still within the realm of time. And that's it for outside air units. Hope that was helpful. Outside air is a little different when you look at it, but still the same basic sequences and process. Really appreciate you watching the video and patronizing my site. I appreciate that. Please have a great day, and I'll catch you on the next one. Thank you.